Hello. Not too many people today. Okay. Oh, okay. Getting better. Right. Okay. So who's managed to have a look at assignment 6 physics, magnetism? Who's had a glance already? You can say no or yes. Okay, good. Good. So you had a glance. So it won't be published. That's fine. I only published it like an hour ago or something. So that's fine. It's finished. I'm doing a final proofread and it will be published tomorrow morning, the latest. Let's put it this way. Maybe tonight. But the problems are already there, so you can start the problems. It's a small assignment, and we only give you a week and a half to do it. So very sorry about that. Otherwise, we just run out of time. So you'll have this and next weekend to do it. So just keep that in mind. All right. So the topic is magnetism, and it's an amazing topic, like honestly. So we start with some magnetic forces. And so magnetic forces. Like this. And magnetic force is QVB, which is you should be already be familiar with it. Are you familiar with the formula QVB from school? F equals QVB. Yes, no, yes. Good. Okay, so yeah, pretty much as expected. And but of course you would know the formula BIL. F equals BIL. Where is it? QVB. Well, BIL. You would know it from GCSEs. Then we have movement of particles in a magnetic field. So they follow circular paths, and this is how particle detectors work. We can tell whether something is an electron or a positron, for example, or a proton. So there's particle detectors and particle accelerators, of course. Then we discuss the Hall effect, which is quite an interesting thing to do. And then what happens is we go into something new, something completely new to you, which is the Biot-Savart law. This is similar to Coulomb's law, if you think about it. Like for the Coulomb's law, if you take a charged particle, and if you have a charged particle, let's say plus Q, and it creates an electric field around itself. And if you want to find the electric field at any point, you just need the distance to that point. So the electric field at that point would equal to 1 over 4 pi epsilon naught. 4 pi epsilon naught multiplied by Q over R squared. Okay. This is the electric field created by a point charge. And if you look at this formula, this is the magnetic field created by a small section of wire at a point. So this is the electric field at point P, and this is the magnetic field at point P. So quite quite interesting. So you can find you can see that these formulas are very similar. There's the current and the length of the wire. They multiply the current by the length of the wire. Then then you divide by R squared, which is the same thing that you do here. Okay, so that's quite interesting. This is the magnetic field created by a very small section of wire. And then we go into some integrations and just more more examples of the Biot-Savart law. All right. If you are observant, you would see this in the Biot-Savart law. You would see this structure. What does that mean? Can somebody tell me? You can ignore the D. It is the cross product. Yes, by all means. Are you familiar with the cross product? Noah, Edward, and who else is in the? Oh, okay, Edward, Noah, Edward, Judah. No, okay. Cross product is a way of multiplying vectors. It's also known as the vector product, cross product, or the vector product. So I'll just make a note of this. This is the cross product, or vector product. It's a vector product of two vectors. Well, and this is what we're going to start with. A little bit of maths. So we have the scalar product of two vectors, which you're familiar with, scalar product. So A dot B, also known as the dot product. And that's defined as the modulus of vector A multiplied by the modulus of vector B multiplied by cosine of the angle between them. Okay. Why is it called a scalar product? Can somebody tell me? The result is a scalar. Yes, the result is a scalar. Because modulus of A is a scalar, modulus of B is a scalar, and cosine is a scalar. So multiplying two vectors, you get a scalar. And interesting properties. If the angle is 90 degrees, if theta is 90 degrees, the dot product is 0. This does not happen to the cross product. So the vector product or the cross product it's written like this: A cross B. Now the formula is very similar. In fact, it's modulus of A multiplied by modulus of B multiplied by sine of the angle between them, B. But that only gives you this only gives you the modulus of the gives you the modulus of the vector, because a vector product, the result is a vector. So if I write like this would be true. But well, not exactly, because sine can be negative technically. So can sine be negative? Well, no, sine, the angle between two vectors cannot be negative. It cannot be more than 180 degrees. Sorry. So yeah, this would work. This would be true. But if by adding here n, a vector n, right, and what n is a unit vector found using the I usually forget. It's the right-hand rule or the left-hand rule. It's using the right-hand rule. Right-hand rule. Using the right-hand rule. So this is the right-hand rule. So you draw the vector A, and it follows your index finger. That's vector A. Then vector B follows your middle finger. And the thumb is the vector N. Okay? It's a normal vector. It's always 90 degrees to vectors A and B. And the result is a vector. So that's why it's called a vector product. Okay. So let's try to find the vector product using the definition by this. So we have A, we have B. So it would be nice to have a diagram. So let's draw. As standard, we draw X in this direction, Y in this direction, Y in this direction, and Z in this direction. So vector A is 3, 0, 0. So it's like this. This is vector A, which is 3, 0, 0. We draw vector B, and vector B is 2, 2, 0. 2, so 2, 2, 0. 2, 2, 0. That's vector A. That's vector B. Now, using your right hand, your A points along, your index finger points along A. Your middle finger points along B. And which way your thumb points? Somebody tell me. Give it a go. The positive Z or negative Z. So up or down. It's always going to be Z. I mean, it's always going to be perpendicular. It's positive Z. So yes, the vector N goes in the positive Z direction. So Noah, Judah, well, everyone else. How well do you understand what's going on here? Do you understand how I found the vector n? Yes. I'd like an answer from everyone, so please let me know. Do you understand how I found the vector n? And I can write down that vector n is 0, 0, 1. Because it's a unit vector. So by definition, n is a unit vector. Cool. So now I use the definition. So the cross product, if I use my left hand, then the answer would be all the opposite. It would be down. Okay. When I was at university, I learned it differently. What we said, we look from the z-axis. We look from the tip of the z-axis. So our eyes looking at the z-axis, and the angle A to B should turn anti-clockwise. So if we're looking from the top, if we're looking from above, A to B turns anti-clockwise, and that's how we determined the whether it's correct or not. But this way it's the right-hand rule. So it's by definition. Okay. So A times B, vector A times vector B, is the modulus of vector A, which is the modulus of vector A. Well, let's write it down. Times the modulus of vector B multiplied by the sine of the angle, sine of the angle between them. So you will need this angle, theta, multiplied by vector n. It's a hat because it's a unit vector. So modulus of vector A, well, it's easy to calculate. It's 3. Modulus of vector B is 4 plus 4, so that's 8. That's square root of 8. Sine of the angle theta. Angle theta. Can somebody tell me what's angle theta? You could always use the scalar product to find the angle, but do you need to? Do you actually need to use the scalar? Well, I mean, you don't need, in this particular case, you don't need to use the scalar product to find the angle. You will in the assignment. Somebody tell me what's the angle between vector A and vector B? I give you a hint, and my hint is that it's an easy question. It's an easy angle. Try drawing it on a 2D plane. Draw it on the XY plane. (45°). Well done. Yes, it's 45 degrees. Okay, is everyone convinced that it is 45 degrees? Is there anyone who does not understand that it's 45 degrees? If you draw it on the XY plane, it's going to be 45. Right. I'm happy to explain why. Just you need to let me know. Otherwise, I assume you understand. It will take me like 20 seconds to explain. Okay. So I assume you understand why it's 45. So sine 45, as we know, it's square root of 2 over 2. And the n vector is, I'm going to write it as a column 0, 0, 1. And that's it. So the vector is, this is 4 divided by 2, 6. So the vector is 0, 0, 6. It's quite cool. Another thing, another property of this, that if you draw the vectors A, and you draw the vector B, vector A and vector B, and you draw a parallelogram, the area of the parallelogram, well, if this angle is theta, that means that this altitude, h, is going to be modulus of b sine theta. So the area is modulus of A, modulus of B, sine theta. In other words, A, the cross product of A times B, is equal to the area of the parallelogram, parallelogram. Okay. And the second way of finding, we can just use the definition. So we have vector A, which is 3, 0, 0. We have B, which is 2, 2, 0, 2, 2, 0. And we have CX, which is AY, BZ. So AY, BZ, that's 0. Minus BY, AZ, that's 0. This is AZ, BX, so that's 0 times 2, that's 0. Minus BZ, that's 0 times 3, 0. So that's 0, that's 0. And that is AX times BY, which is 6, minus BX, which is 2, times AY, which is 0. So that's equal to 6. And that's our vector, our resulting vector, 0, 0, 6. Okay. And there's a third way of doing it. So the third way is basically the second way, but more elegant and easier to remember, because I mean, probably I had one student in my oh gosh, in my 17-year teaching career, I had one student who would easily remember this formula. He would just have a look at the formula and remember it, and 5 years later he'd still remember it. He had a phenomenal memory, but I would never remember this formula. So I don't like formulas that are difficult to remember. So you can just say, if you have vector A, which has coordinates A1, A2, A3, and you have vector B, which is B1, B2, B3, then the cross product of the two vectors, A times B, is the determinant of a matrix. So next assignment is going to be matrices. And here we have I, vector I, vector j, these are unit vectors, and vector k. And here we have a1, a2, a3, b1, b2, b3. It's the determinant of the matrix. Who has done 3x3 determinants? Have you done 3x3 determinants? Yes, yes. Not yet. Okay, some of you have, some of you haven't. All right. Okay, so about 60% of you have, which is good to know. The determinant of a 3x3 matrix. Well, I'm going to do an example. Because we know A and B. So A is 3, 0, 0. So 3, 0, 0. Cross product 2, 2, 0. 2, 2, 0 is the determinant of this matrix. I, J, K. 3, 0, 0. 2, 2, 0. So these are vectors, of course. So we do vector I multiplied by the determinant of this matrix. So I multiplied by 0 times 0 minus 0 times 2 plus j. I'm not sure why I'm doing this, because those of you who haven't done determinant, this would be super confusing. And those who have would look that I'm just wasting time. Anyways, minus j times 3 times 0 minus 2 times 0 plus k 3 times 2 minus 2 times 0. And you will see that the answer is 6k. 6k, or in other words, 0, 0, 6. This is by far this is my favorite way of finding the cross product if you know the coordinates. Because if you don't know the coordinates, this is useless. You need to use the first definition. Okay, the modulus in the angle. Now, I'm not a fan of this formula. If you look at this, so why so? Because this bit is quite confusing. But this it mustn't be. It mustn't be confusing. See, this is just tells you that the modulus of the vector can be found by this. And the direction, this only gives you the direction. The direction is always perpendicular to the first two. So if you have two vectors like this, for example, the third vector is always going to be perpendicular to the two. Okay. If you have vectors like this, the third vector is going to be like this. Always, it's a normal vector. That's why we denote it as n. The denotation is n, because it's normal to the plane containing the two original vectors. Does everything make sense so far? I mean, if you haven't done determinants, don't worry, you will. And you will do them in the next maths assignment, maths 07. Otherwise, ask me a question. Ask me a question if you don't understand. Okay, so a particle in a magnetic field, we already know, experiences a force. A particle in a magnetic field. Magnetic field experiences a force F equals QVB. Now, The only thing is, that's not the one. So it's like this. So the grown-up version is a vector. V is a vector, and it's a cross product times B. Okay, so I'll just rewrite it because I don't like the arrows. So vector F is equal to Q V times B. So it's a cross product. Yes, so that's what I want to say. The force on a particle is the cross product. And as you can see that if the velocity goes this way and the field is perpendicular, and the field goes like this, for example, goes like this. So this is the velocity and this is the field B. The force would be perpendicular. And you were taught in school, you were taught that you use the left-hand rule to find. So the first finger is the magnetic field. The second finger is the direction of current. So it's a positive particle, it's this way. If it's a negative particle, you need to reverse it. And the thumb indicates the direction of the force. So the force in this particular scenario would be out of the page towards out of the page. So the force out of the page. Yes, is everyone familiar that this is out of the page, this is into the page? Yes? Tell me a yes or no, please. This is out of page. Okay, so for Edward, just think, we live in a three-dimensional world. So we have 6 different directions in which we can move. We can move right, we can move left, we can move up, we can move down, and also there's a third dimension, which is out of the page towards your face. So this is towards your face, and this is away from your face, or in other words, out of the page into the page. Out of page into page, into the page, the page. So why is it so? The answer is simple. Arrow archery. Image. So if you are this lady, if you are this dangerous looking lady, what you see as the arrow moves away from you, what you see is the feathers of the arrow. So you see a cross. So arrow moving away, moving away. Okay. And If you're this lady standing with an apple on your head, what you see is an arrow moving towards you. And you see the sharp end of the arrow. Yes, you see the sharp end of the arrow. This is arrow moving towards you. Towards you. Okay. Make sense? Sorry, wrong button. Okay. Good. Right. So we can find the force, and we know that the force is always perpendicular to the movement, to the velocity. So in this case, so if you have a magnetic field going into the page, just as it is shown in the diagram, and let's say you are here and you're moving that way, velocity, and B is going into the page, the force would be perpendicular. Force is like this. Like, this is quite easy to show that it is perpendicular, and this will be one of the questions in the assignment. You will need to say that the force is perpendicular. Now, what happens, because that's the only force acting on the mass. So you have a mass here, and you write down F is equals to QVB. And but F is also the centripetal force because it is moving in a circle. So it's mv squared over r is equal to QVB. Therefore, we can work V cancels, and we can work out the r. The radius of the path is mv divided by QB. And this formula is in a way brilliant. So what happens if you have a heavier particle? What happens to the radius if the particle is heavier? Just look at the formula. If you have a more massive particle, it will take a bigger radius. Yes, if you have a heavier particle, so a lighter particle would go like this, a heavier particle would take a bigger radius, which makes perfect sense. If you have a faster particle, it will have a bigger radius. If you have a more charged particle, it will be more affected by the magnetic field, so the radius would be smaller. The more the charge, the smaller the radius. Finally, if you have a stronger magnetic field, B, you would have a smaller radius. So this formula makes perfect sense. So the question is, an alpha particle and a proton are accelerated by a voltage 2 kilovolts, and they enter the magnetic field. This is the magnetic field, and they land on the screen. So you can see that one particle lands here, and the other particle travels this way. Okay. So which one do you think is which? Which is the alpha particle and which is the proton? The crosses on the diagram represent the magnetic field. Magnetic field going into the page. Bigger radius. That is half. This answer is half correct because they don't have the same speed. Let's work it out. So find the speed of the particles first. So they're accelerated by a voltage of 2 kilovolts. So this is the kinetic energy. So the kinetic energy is going to be equal to the charge times the voltage. So it's Q times the V. So it's 1/2 mv squared is equal to QV. That's the accelerating. That's the accelerating voltage. So we can work out V is equal to 2QV divided by M square root. Okay, that's the speed. And the speed of the proton is going to be, well, we don't need that yet. That's the speed. Now we know that the radius of the particle is mv divided by qb. So we can sub that in. So m qb square root of 2qv, which is capital V, that's the voltage, divided by m. Oh, m cancels out. So we have m, so it's an m like this. Okay, so it's square root of 2qvm divided by qb. Oh, q cancels. Well, okay, we'll get back to that as r. And the distance from the entrance. So we have a small particle. We have a particle entering. We have a small particle entering the magnetic field. It takes a radius, so it makes half a circle. So the distance is 2r. So how far from the entrance will they land? So 2r, so the distance, I don't know, x1, sorry. X is the distance from the entrance, so that's x. Right. X is 2r, so that's equal to 2. So 2. Yeah, just need to simplify that. Well, it's going to be square root of, yeah, just let's make it a single square root of 2q voltage m. Oh, that's going to be 8 because of the 2 we multiplied by 2, 8 divided by q squared b. So q b squared, and there's no q here. 8Vm over QB squared. That's the distance from the entrance. So we find it for the proton, and we find it for the alpha particle. And let's see. So it's square root. Let's finish this problem. So for the proton, it's 8 multiplied by 2000. That's the voltage. Multiplied by the mass of the proton. The mass of the proton is 1.67 times 10 to the minus 27. and divided by QB. The charge of the proton is 1.6 times 10 to the minus 19. And B is 0.2 squared. So that is 8 times 2000 times 1.67 times 10 to the minus 27. 1.6 times 10 to the minus 19. 1.6 times 10 to the minus 19 times 0.2 squared. 0.065 meters, which is 6.5 centimeters. 6.5 centimeters. And for the alpha particle has 4 times the mass, and 2 times the charge. Everything else is the same. So it's going to be 0.0913. 0.0913 meters, which is 9.13 centimeters. So I suspect it's square root of 2 times bigger. So divided by square root of 2. Yeah, it's square root of 2 times bigger. So that is the alpha particle. This is the path of the alpha particle, and this is the path of the proton. Okay. So the alpha particle would take a bigger radius because it is heavier, but it is slower, but it is it's square root of 2 times slower. So yeah. So it's accelerated by the same, they have the same kinetic energy. That means the alpha particle is slower. But then it has a larger mass, so it is less deflected, and it has a larger charge, so it is more deflected. So there's several factors in play here. Now, the Hall effect I wanted to talk about, and okay, oh, we don't have that much time. The Hall effect. So imagine you have a plate with a current flowing through. Let's say you have a conductor. And you have a conductor in the form of a cuboid. Right. And you have a current flowing through. So let's say it's connected by a wire like this to a battery. Let's say like this, battery plus minus. So you have electrons flowing through the conductor. Electrons. Flowing through. Now, if you introduce a magnetic field, let's say you have a magnetic field going this way. Or in other words, just going into the page. Yes, so magnetic field. What would happen to the electrons? What would happen to the moving electrons? go down. They would, Adam. Well, yes, by all means. Use the left-hand rule, right? So they would be drawn down. So there would be a force on the electrons, causing them to push down. There would be a force. Okay. That means that the bottom of the conductor would become negatively charged. Because there would be more electrons. There would be an excess of electrons on the bottom side. But this excess of electrons would mean that they push there's an electric, and there would be a lack of electrons on the top, so the top would become positively charged. But that would mean that there's also a vertical electric field inside the conductor. There would be an electric field which would push the electrons up. Just like a capacitor, yes? Top is positive, bottom is negative, and you have an electric field inside. The electric field pushes the electrons back up. Moving electrons experience a downwards force. F equals QVB. Then there's an excess of electrons on the bottom and lack on top. That means electric field, a downwards electric fields. Downwards electric field inside conductor. Conductor E. And upwards force on electrons from electric field. Okay, so the upwards force equals E times Q. E times Q, and because they are equal, we have QVB. V is equal to EQ. Now the electric field, and we know that in a uniform electric field, if this is the distance between the plates, we know that E is equal to the voltage between divided by the distance. So we can incorporate that, and we know that we also know that the speed of the current in the conductor is Q N A E V. Oh, so not Q, sorry, NAEV. This is from A levels. You should know this. If you don't, look it up. please, and by the velocity. So velocity is equal to I divided by NAE, where N is the charge carrier density, A is the cross-sectional area, E is the charge of one electron. So we can write this down. So E times V, which is I, divided by, so E times I divided by NAE multiplied by B is equal to E, which is the voltage on the top and bottom, voltage between the top and bottom, divided by the distance between, and multiplied by E. And you see that a bunch of stuff cancels, well, not really. We know that the voltage is equal to, so fraction E cancels, I, B, D divided by N, A, E. Yes. I hope I didn't mess it up. That's the voltage. If you connect a voltmeter on the top and bottom, if you connect a voltmeter on the bottom and top like this, what you can do is you can make a device that that measures a magnetic field. Okay, it's called a Hall sensor. This is the Hall voltage. This is known as the Hall voltage. And this is the device is called a Hall sensor. Measures magnetic field. So how does it do that? Well, we measure the voltage by measuring voltage. So you measure the voltage between the top and bottom, which is caused by the magnetic field pushing the electrons down. There's a disbalance between electrons and protons on top and bottom. So we have a negative charge on the bottom, positive on top, and we can work out the magnetic field from here. Does that make sense? Anything you'd like to ask? Please ask. I like when people ask questions. If you made the conductor hollow, is that how you make the velocity selector in a mass spectrometer? Well, here it is just like a velocity selector, except it will always adjust the electric. It will automatically adjust the electric field so that they always move straight. But the velocity selector works, it has the same principle. You have the same two forces. The velocity selector, you have a charge and you have a downwards magnetic field, and you have an upwards electric field. And yeah. So if you made a conductor hollow, if you made the conductor hollow and you introduced an electric field, yes. Okay, if that makes sense. To make a velocity selector, selector. So you have two plates and the bottom plate, and you control the charge on those plates. So basically you have a set voltage. So it's a variable voltage. You just connect it here. So one plate is positive, one plate is negative. So let's say the top plate is positive, the bottom plate is negative. And you have a magnetic field in this direction. And you have a particle entering, a charged particle traveling with velocity v. So that's a charged particle. And you have an upwards force, which is you have a downwards force, which is the electric force, no, magnetic force, and the upwards force, which is the electric force. The electric force is QE, and the downwards force is QVB. So the velocity is equal to QE divided by QB, QE divided by QB, Q cancels, is E over B. So why is it a velocity selector? It only allows particles with only particles with a set velocity will go straight. Okay, and these are used in mass spectrometers because for a mass spectrometer you need the particles to have the exact same speed every single time. Selects. If you don't know about the velocity selector, please look it up because these are astonishing. Like, I mean, just ingenious how people worked them out. What else? Problem 4, an electron enters a magnetic field. At point A, the velocity is v. The distance between A and C is L. The distance is L. And what is the magnetic flux density if the electron passes through point C? Ideas. How will the electron move? First of all, it's a difficult question. I didn't put into the assignment because it was too complicated. But there is a somewhat similar question there. It's less. How will the electron move? Which way would it be pushed? Okay, Adam thinks it would arc up and then down through C. I wouldn't call it arc. It would go up and then through C in a way. But Okay, let's say the particle, let's say alpha was 0. What would happen if alpha was 0? If alpha was 0, how would it travel? Why? Would you be able, Adam, would you be able to switch on the mic and explain why? You're correct. No. If you're saying something, we can't hear you. I assume. Right. So V is okay. Yeah, B is parallel to V because B times V, the modulus of V multiplied modulus of B multiplied by sine sine theta times the n, but this is going to be 0. So if alpha was 0, if alpha was traveling, if it was traveling like this, it would just carry on in a straight line. What would happen if alpha was 0? If alpha was 90 degrees? If alpha was 90 degrees, how would it move? Very good. It would circle out. So if we look from the back, if we walk here, and we look from this direction, what we would see a magnetic field like this. Magnetic field going into the page, going away from us. Yes, so arrows flying away from us. You would see a magnetic field. And you see a particle moving up. You would see a particle moving up. And because it is an electron, we use the left-hand rule to find the direction of the force. So the field is that way. The current is down, therefore the force is to the right. So this is the velocity, and the force is to the left. Therefore, it would travel like this. Particle would make a circle, a full circle. So what happens is, so it would travel towards us. So A would go up and towards us, and then it would go down and towards us. Then it would go down and away from us. So it would make a circle. So A would travel in a circle like this. So if you see me, do you see me? Yes, you should see me. So it would travel like this. So if it's traveling like this, I'm going to use my duck. So the electron is traveling like this, but also it is traveling sideways. So it's going like this. So what kind of movement is this? What do we call that? Yeah, helix, spiral. So what happens is the electron would travel like this, make a spiral, and then travel to C. Right. And the radius of this spiral is, as we already know, is mv divided by v perpendicular. So v perpendicular divided by qb. And the horizontal movement, the horizontal speed is v parallel. Okay. So the time it takes, time to travel from A to C. So you need is the distance L divided by the speed parallel. So the particle has two velocities: the velocity parallel to the magnetic field and perpendicular to the magnetic field. So I'm calling this V perpendicular and V parallel. V parallel, so that's equal to L divided by V cos alpha. That's the time to travel horizontally. Time to make a loop. Time. Oh, well, we don't know. It could make several loops. Yeah, it could go like this, do one loop and go one loop and stop, or it can do 17 loops before reaching C. Okay. So time to travel K loops of radius R. Radius R. Well, we know that the distance that you need to travel is 2 pi r k, and the speed that you're traveling with is v perpendicular. Okay, so it's 2 pi k multiplied by r, and the r is m v perpendicular, divided by v perpendicular qb. You can see the v perpendicular cancels out. So it's 2 pi k m divided by qb. All right. So the particle makes a helix, or k loops before reaching point C. And then these times are equal. So L divided by V cos alpha is equal to 2 pi k m qb. And what are we looking for? Oh, we're looking for B. So B is equal to 2 pi k m v cos alpha divided by L. LQ. LQ. Okay. Right. How are you finding this topic? 10, you understand completely. 1, you are struggling to understand. How are you finding the topic overall? Not particular questions, but the topic. 9.14. Okay. Right. then we move to the Biot-Savart law, and we can work out the field from an infinite conductor, for example. So how does it work? Well, we have the field, the magnetic field, from a small section of wire. DL is a section of wire located at a distance r from a given point, produces a magnetic field, which has this is the formula for the magnetic field. For a small segment of the wire. So let's see if that makes sense for a single loop of wire. Let's say we have a loop of wire, just like in a solenoid, and there's a current flowing in the wire. And let's look at a small section of that wire. Section of that wire, DL. It is convenient to use the angle, and let's say we start from here, and this angle is going to be theta. Okay, then the radius, and let's for simplicity say that this is x and this is y. So dl is a vector. dl is a vector, and it's equal to, it's going this way, so the current is going this way, so it's dl, so that is theta, so that is dl sine theta and dl cos theta, and 0. That is a vector. Now the radius, the vector drawn from the vector r. I think I'm overcomplicating things here. Well, let's see where this where this method takes us. The radius drawn from this particular point to this point is going to be minus the radius of the loop times cos theta, sorry, and minus r sine theta, because is going downwards, and we need a unit vector. So the unit vector is going to be 1 over r, because we know the length of this vector is the radius of the loop. 1 over r times that, therefore is just simply n0. So it is minus cos theta minus sine theta 0. My intention was to do it slightly differently, but let's see what we have. And okay, so we have the dB. dB is mu0 divided by 4 pi multiplied by the current. Current is fixed. Well, multiplied by dl. So divided by r, the radius squared, the radius of the thing, multiplied by the product of dl and r. So dl sine theta, dl cos theta 0, cross product minus cos theta minus sine theta 0. Okay, so dl kind of goes out. So dl, we can take this out, and we have sine theta. So we have the cross product of I, j, k, and we have sine theta cos theta 0, and we have minus cos theta minus sine theta 0. We find the cross product of that. So it's I0, J0, so it's K multiplied by minus sine squared theta Oh, that's very unfortunate. Yes, because I've made a mistake here. It's going to be minus dl sine theta, minus dl sine theta. So minus sine theta. So plus sine theta plus cos squared theta. And that's 1. So that's just k. That's fantastic. So this whole thing, so that's equal to 0, 0, 1. So this is mu0 I divided by 4 pi r squared dl, and then dl multiplied by 0, 0, 1. And then we can remember that dl is in fact equal r multiplied by d theta, by the angle, because the this is the length of arc. This is the length of arc, so that's equal to mu0 I 4 pi r squared r. Sorry, this is r squared r d theta, and then multiplied by 0, 0, 1. All right. So overall, if we take if we integrate this now, if we integrate this from 0 to b, and this we integrate from 0 to through the whole circle from 0 to 2 pi, so 2 pi radians. Okay, and we get, because these are constants, so we have 0, 0, 1 multiplied by mu0 I 4 pi r squared multiplied by 2 pi r. 2 pi cancels, we have 2, r cancels, is equal to mu0 I divided by 2 pi. And this in fact is, sorry, 2r. What am I doing? 2 front 2 pi 2r. 2r. This is the magnetic field inside. So this is the magnetic field at the center of a single loop of radius r carrying current I. So the magnetic field at this point is equal to mu0 I divided by 2r. Okay, so I apologize for my clunky explanation. And the 0, 0, 1 vector simply gives you the direction of your vector. Yes, so B is that, but if you want a vector, vector B is going to be mu0 I divided by 2r 0, 0, 1, which makes perfect sense. I'm afraid to ask how much sense this question makes, but I will. So tell me, how much did you understand from this clunky explanation? Silence. On a scale of 1 to 10, please. So yeah, as long as you're comfortable with the vector product, yeah. But you can do it. You can do it way easier. You can say, okay, there's a circle, and there's a small section of wire dl, and then the distance is r. But we know that the current is always perpendicular to r. So if we want the dl multiplied by r, well, that's simply going to be dl multiplied by r divided by r. So just dl. Okay. And then you use b is equal to, well, db dB, the Biot-Savart law, B becomes mu0 divided by 4 pi multiplied by I dl over I dl over I dl over r squared. Oh yeah, yeah, dl over r squared, and then you integrate that. You integrate that from 0 to b, and you integrate that so from 0 to 2 pi r, because that's the length of the thing. So you get so from here you get b is equal to mu0 over 4 pi. That's a constant. 4 pi. I is a constant. I, and then 2 pi r divided by r squared, and all that cancels out to mu0 I divided by 2r. So you could do this simpler. You can realize that dl, that this thing is dl, and then you just integrate it. Okay, and here we have the magnetic field of an infinitely long wire carrying a current, and I'll leave this to you to explore. Okay, so I will publish this tonight or tomorrow morning, and yeah, so enjoy, Have a great time with Biosavart and magnetic fields. I hope you enjoy it, and see you next week.
Can I just ask a quick question
Yeah.
about the right hand rule?
Yeah.
You mentioned earlier, you know, when you were doing problem 1 and you drew that diagram with the vectors, vectors A and B are not perpendicular to each other. So, but if I take my right hand and I position my hand as shown, it indicates that A and B are perpendicular to each other.
They don't have to be. They don't have to be. The thumb is always perpendicular to the fingers, to the plane of the other two fingers, but the two fingers don't have to be perpendicular. They could be an acute angle or even an obtuse angle like this. So it doesn't matter.
Okay, fine, but it's only the thumb that has to be perpendicular.
Yes, the thumb
Okay.
has to be perpendicular to both A and B.
Okay, thank you.
Okay. Right, that's why we call it normal. It's an n normal vector. Okay. All right, see you.